Hello everyone and welcome back to the course. Today, we are diving into the fundamentals of set theory, from understanding when two sets are equal to exploring subsets, the mysterious empty set, and the overwhelming power set. Off we go. We have intuitively used the symbol of equality between sets, but now we are going to define it formally. We say that two sets are equal if they contain the same elements. In other words, if two things happen. The first one is that every element of A belongs to B, and the second one is that every element of B belongs to A. If either condition fails, then the two sets are not equal. For instance, if we have the set A with elements 1, 4, and 5, and the set B with elements 4 and 5, we can notice that every element of B belongs to A, but there is an element in A, which is 1, that belongs to A, but it doesn't belong to B. Therefore, these two sets are not equal. Let us consider the following example. Consider the sets A with elements of the form 2n cubed with n, a natural number, n between 0 and 3, including these two numbers, and the set B, which elements are 2, 0, 16, and 54. Now, in order to check if A and B are sets that are equal, we need to list the elements of A. In other words, we need to define A by extension. If we do so by substituting each of the elements of n, which are 0, 1, 2, and 3, into the first expression, 2n cubed, we get the elements 0, 2, 16, and 54. Since A and B contain the same elements, we conclude that A is equal to B. Now it is time to introduce a very important set, a set with no elements. This set is called the empty set, and it plays the same role as 0 in the set of real numbers. This set can be defined in many different ways. For instance, the set of all natural numbers n, such that n is between 1 and 2. We know that we don't have natural numbers between 1 and 2, so this set is empty. As well, the set of all real numbers x, such that x squared plus 1 is equal 0. We know that this equation does not have solution in the set of real numbers. So this set is also empty, and we will represent this with the following notation. Now, another important concept in set theory is the concept of subset, which is closely related to the concept of set equality. We say that a set A is a subset of B, or that A is containing B if every element of A belongs to B. If there is at least one element in A that does not belong to B, then we say that A is not a subset of B. And we will use the following two notations for determining when A is a subset of B and when A is not a subset of B. By inspection, we can verify that the set with elements 1, 3, and 4 is a subset of the set with elements 1, 2, 3, and 4. As well, we can notice that the set of all natural numbers is a subset of the set of integers. This one is a subset of the set of rational numbers, and this one is a subset of the set of real numbers. Let us consider the following example. Consider the sets A and B, where A is the set of all natural numbers n, such that n times n minus 1 times n minus 2 is equal 0, and B is the set with elements 0, 1, 2, 3, and 4. We find that A can be expressed by extension, and all of its elements are 0, 1, 2. And since A is containing B, meaning all elements in A are elements in B, we can say that A is a subset of B. Nevertheless, 4 is an element of B that is not in A, so B is not a subset of A. Now, an important remark that we have to make about subsets is that they satisfy the following properties. The first one is that the empty set is a subset of A no matter the set A, and that the set A is a subset of itself. As well, we can redefine the concept of equality of sets in the following way. If we have two sets, A and B, we say that these two sets are equal if and only if A is a subset of B and B is a subset of A. Something quite curious and remarkable about sets is that sets can contain sets as elements. For instance, let us consider the set which elements are the set of natural numbers, the set of integers, the set of rational numbers, and the set of real numbers. This is a set which elements are sets, and this set has 4 elements. Of course, among all of these sets, which elements are also sets, there is one which is the most important among them, and this set is called the power set. We define the power set of a set A as the set which elements are the subsets of this set A. We denote the power set of a set A as P of A, and we define it like this by using comprehension, meaning this set is equal to the set of all sets B such that B is contained in A. Something remarkable that we have to establish about power sets is that given a set A, the power set of A is never empty, because given this set, we know that the empty set is a subset of A and therefore is an element of the power set of A. As well, given this set A, we know that A is a subset of itself and therefore is an element of P of A. Let us consider the following examples. In the first one, we are going to take the power set of the empty set, meaning P of the empty set. Now, this set has only one element because we know that the empty set is a subset of itself and therefore is an element of P of the empty set. In the second example, we are going to consider the set with one element, which is the number 1. Its power set is the following: the empty set and the set that contains 1. This happens because, as we mentioned before, the empty set is an element of any set, and the set that contains the number 1 is a subset of itself. In our third example, we have a set A with 2 elements, the number 1 and 2. And the subsets of this set are the empty set, the set that contains the number 2, the set that contains the number 1, and the set that contains the number 1 and 2, meaning the set A. Let us consider another example. In this case, we are going to consider a set A with 3 elements, A, B, and C. And the power set of this set is made of all of the subsets of this set, which are the empty set, the set which contains the letter C, the set that contains the letter B, the set that contains the letter A. Then we have the sets that contain the letter B and C, and also the set that contains A and C, as well as the set that contains the letter A and B. And finally, the set A itself, meaning the set that contains A, B, and C. Notice that if we start counting the number of elements of each of the power sets that we presented in the previous examples, this number grows exponentially by a factor of 2. As a matter of fact, if we have a set A with n elements, then the power set of this set will have 2 to the n elements. Therefore, if we have a set with 5 elements, then the power set of such a set will have 2 to the 5 elements. One more thing that we need to know about powered sets is that we are not limited to take the power set of a set only once. As a matter of fact, we can apply this repeatedly. But the thing with this is that it grows even faster. For instance, if we have a set A with 2 elements, then the power set of the power set of this set will have 2 to the power of 2 to the power of 2 elements, which is equal to 2 to the 4, and this is equal to 16. Well guys, this is all for today. I hope that you enjoyed this lesson. Now you are one step closer to master set theory. In the next chapter, we are going to check on operations on set theory. See you in the next lesson.